Well, hello everyone, and thanks for tuning into this presentation. My name is Lance Conway. I'm a grad student at Mizzou in the Soils Department. I'm working under several USDA ARS scientists, Drs. Kitchen, Sudduth, and Voorhees. And the project we're associated with is some planner sensor work. And really what we're trying to understand is how accurate and consistent these sensors are and whether or not they can really be used to guide agronomic decisions. And so when we think about a modern row crop planner, the technology available on these planners is pretty substantial. And it can almost be overwhelming as an operator in the cab how many data layers we're actually collecting. And part of that reason is because, this is no longer a 24-row planner. Even though all these row units are connected to the same toolbar, each one is acting independent of its neighbor. So whether it's seeding rate or the amount of downforce it's applying, all that information is being collected on a row-by-row basis and controlled as well on a row-by-row basis. So what that results in then when we're doing things on a row level is a lot of information. With one pass through the field, we're collecting a lot of data. And so we really wanted to understand how can we best use this and what tools available to us currently are the most useful. And so one technology that we were most interested in was the Smart Firmer from Precision Planting. And I think it's a tool that at least aims to merge that agronomy with the technology, because that's one thing we got to keep in mind as this technology advances, whether it be on a planner or another implement. We can't let it get too far ahead of the agronomics or the science. They need to move together. And when we think about the Smart Firmer, well, what exactly is it? For anybody that hasn't seen one, it's basically a Keaton seed firmer with a couple sensors on it. And so it has an optical portion that emits and detects 5 different wavebands of light. And it also has a thermopile sensor, which measures soil temperature. And from those 2 sensors, we're getting this suite of metrics here: clean furrow, furrow uniformity, temperature and moisture, as well as OM and CEC. And all of those except for temperature are coming from the optical portion. And some of these are designed to be more of an in-cab diagnostics, like the clean furrow might help you set your row cleaners. But other metrics like the moisture, OM, and CEC can be used to guide on-the-go variable rate applications. So for example, the organic matter could be used in conjunction with the V drive to change seeding rate on the go. So the Smart Firmer you see there down below the gauge wheel is working in conjunction with that electric drive. And same thing for the Smart Depth system, except for that, they're using furrow moisture to guide planting depth. So that kind of gives you an idea of the difference in how these metrics are being used. And so the 2 main objectives we had were, one, are they accurate? So if we get a soil organic matter estimation in the trench, how is that going to compare to a soil sample that we take and send off to the lab? And then the second part of that is it repeatable? So whether or not that it can predict true organic matter, can we at least get the same map twice if we plant a field a couple times within a year? And then the second objective is what's actionable? What can we really take from these that we can confidently say, yes, this is a good metric to use to guide planting depth or to adjust your row cleaners or for whatever our objective is there. And so jumping right into the results, this is some performance work that we've done. On the left, we've got our Smart Firmer organic matter, and on the right, we've got lab measured organic matter from soil samples. And what you'll see is that they follow similar spatial trends. So what's low is low and what's high is high for the most part between the maps. But what you can't really identify until you look at the raw data is the fact that the Smart Firmer isn't quite capturing the range. So this graph shows us that in general, we were overestimating soil OM, and also that slope is not very close to 1. Ideally, all those dots would fall on a 1-to-1 line, but it's not quite capturing the range. And it's basically because we're using a global algorithm, right? Whether you're in Missouri, Iowa, Illinois, and you're using this thing, it's not making any kind of regional or local adjustment. So it's not going to be perfect, but it was promising to see that it at least detected some general differences. The overestimation is probably partially due to the fact that you're looking at the upper 2 inches of the soil rather than that 0 to 6, the traditional sampling zone that we have. So that's kind of helps understand some of the benefits, but also some of the limitations of the sensor. So the next part of this is it repeatable, right? So we took advantage of some prevent plant acres last fall that got flooded out, and we basically had a playground down here in a Missouri river bottom field where we had a real light sand and a real heavy clay on a pretty small spatial footprint, just about 12 or 15 acres. And so this was perfect for us to go down and use this site because it did have a ton of variability, so we could understand the range in soils on a small scale. And so we went down and planted this field 3 times, and that's what you're seeing here. And we had we did it 3 times in 3 weeks, and at each planting date we had a different moisture. So the first planting date was relatively dry. The second week we had about 3/4 of an inch of rain and things wetted up. And then on the third week we just had about 2/10. So it was really kind of landed somewhere between the dry and the wet. So we had 3 different moisture levels for this one field. And the question is, did the change in the environment, did the change in the soil moisture affect how this sensor estimated soil organic matter? Because that is such a popular metric out of these sensors. And so here you can see the OM at the first date, the second date, and the third date. And if you just look at week 1 to week 2, you'll notice those maps don't look all that similar. And what happened is, if you look at the center of the field, you look at moisture versus OM, you can see that as that moisture increased, the estimation of soil organic matter decreased. And so the sensor is trying to compensate for changes in moisture, because obviously the color is going to change of a soil when it's dry versus when it's wet. And so it's trying to account for that. In this scenario, it didn't do so well, or at least it wasn't consistent as the same soil changed in moisture. So just wanted to highlight that the environment is going to affect how these sensors see the soil, and how they, more importantly, interpret the reflectance coming from the sensor. So that gives you at least a little bit of idea of how these things can perform and some of their limitations. But moving on to more of the agronomic side, like I said, they can be used, whether it's organic matter or moisture, to guide on-the-go applications. And we're really interested in the moisture guiding the depth. And so we've been doing some planting depth research for 3 or 4 years now. But this year we kind of ramped up and did it on a larger scale. You can see some drone images there where we've got 1.5 inches versus a 3-inch depth. And you can see the differences in how far along the plants are. You can see more tassels at the 1.5 inches. So differences in emergence early in the year are carrying on later in the year. So hopefully we're going to get some exciting results from this in the fall. But what we have so far, we can see how depth impacted these different seed zone properties. And so if we start with moisture, that's the one we're most interested in. So you can imagine the tractor and planter went across the landscape here. We've got some slope. And so you can see how that elevation changed. And what you'll notice at the 1.5 inches, so the yellow symbols, there was a lower moisture, and there was also a lot more variability in the moisture, as opposed to the 3-inch, which had a lot more. And so I planted each row at a different depth across the planter from 1.5 inches to 3. And I'm just showing you the extreme ranges between the most shallow and the most deep. Moving to temperature, because obviously that's going to be another important component to our germination and emergence. And you'll see that not surprisingly, the 1.5 inches was warmer than the 3-inch. And also you can see that on the south half, or the left part of the field, that soil at the shallow depth had warmed up quite a bit more compared to the north half. So that was kind of interesting to see how slope and aspect may be playing roles in some of this as well. And lastly, you can see the clean furrows, so the amount of residue in the trench. So again, the 1.5 inches had more trash in that seat, in that furrow, as opposed to the 3-inch. So you can see there's trade-offs right? So a shallow depth may be warmer, but it's going to have less moisture and more residue. And so what'll be interesting this fall is we'll be able to actually collect final stand across this entire field. And then we can overlay that final stand with these different metrics to see, okay, was it moisture, was it temperature, was it residue that was really driving emergence and subsequently our final stand. And how we're going to do that is through some stalk counting technology that our research group has. And basically, it's just a rod mounted between the row dividers on a corn head. And that rod is connected to a potentiometer that actually can detect as a stalk goes through the machine. And so what that allows us to do then is get coordinates for each stalk or each plant within a field. And you can see an example of a map here of one we did last year and how each one of those green dots is a plant within that field. And so that allows us to evaluate these things at a much finer resolution. Before we just go out to certain monitoring sites within a field, but now we're going to be able to understand how spatial variability affects it and how they interact across space. And so just to give you a little example of what that might look like, since we're collecting so much data and so many observations in a field, figure each plant's an observation, you're going to have over 30,000 per acre. And so that allows us to just fit these distributions to a field or a treatment to see, okay, how often, how frequently did we get our target spacing? How often did we have a skip? How often did we have a double skip? And that's what each one of those rises in the distribution are. And so this is an example from 2019 to where we compared a low and a high moisture. So we broke it out at 40%. We used some machine learning techniques to say that was our biggest split in the data. So we want to look at how did it affect it if it was wet, above 40 or below 40. And what we actually see here is we hit our target spacing. So every time there was supposed to be a plant there, it was more often at a low moisture, which is kind of opposite of how we might think about variable planting depth. Usually we're wanting to hunt for moisture, but in a year like 2019, it was the exact opposite. It was so wet that the drier we were, the better emergence that we had. And so that just gives you an idea of what we're going to be doing this fall, and we are going to do this down in Portageville. So this is an example of one field that we planted down there where we've got Smart Firmer OM, Smart Firmer Moisture, as well as a yield map from 2019, just to illustrate for you guys how in some cases OM aligns, in some portions of the field. Like you could pick the northeast portion, what's a little bit low there was low yielding. In other cases, the moisture did a little bit better job of understanding that spatial variability. And so we'll want to see how can we combine these metrics to see which ones are really consistently showing up as being correlated to yield and final stand, because we'll have both of those layers down there at Portageville this year. So you can stay tuned. We'll probably be presenting on some of this winter. If anybody's interested, we'd be happy to share some results with what we do down there this year. And so thank you for taking your time out of your day to listen to this. And if you have any more specific questions, we've done a lot of work with this. Obviously, I've tried to condense it down in 10 or 15 minutes, but if you have any specific questions, please feel free to email me, text, or call. I'm happy to share with you what some of the other stuff that we've done with these planter sensors. So thank you.